So here we have section 2.5, implicit differentiation. And this is really just a very handy application of the chain rule. Put that. So, we know how to, we've got a lot of nifty rules for, things like, suppose I have y equals, 3x squared plus 5x, something like that. We know how, we could take that derivative. We say, dy dx is equal to 6x plus 5, right? We just go through and get that done. But now suppose, right, you don't know exactly what y is a function of, but you do know it's a function of x. And so let's look at our prime notation. So remember, if you got y equals f of g of x, right, then what we said was, y prime was f prime of g of x times g prime of x. Well, we're going to switch the notation on you a little bit here because I think that is what can mess people up, is they don't realize, we've been doing this sort of notation with the with that chain rule, but we don't quite use that same notation really when we're doing the implicit differentiation. What happens is all of a sudden you have something like, let's pick a different letter. You have w is equal to some function of y of x, like that. And so then if you say, well, what's w prime? Well, that's the derivative of that outside function and then times y prime of x. Yeah, okay. So see, we might have something like, if I had w was equal to y squared, then w prime, well, actually, at this point, if I actually write this, I should probably be more clear and say dw dx. Okay, because w prime, well, y could be the independent variable, and so w prime might be 2y. Okay, but I'm trying to take the derivative with respect to x, and so it is indeed 2y, but then times dy dx. And if it's very clear you're working with x as the true variable of interest, then sure, you could say, something like w prime is 2y y prime, like that. But that is how we are using this implicit differentiation. So we'll have y and, maybe some function of y, like y squared here. But then the way we'll use the chain rule, you see, is we take that derivative of the outside part, the squaring function. So we brought the 2 down, subtracted 1, got 1, and then multiplied by the derivative of the inside function, which we don't know yet, right? I don't know what that is. But now the way we put that together is, suppose I have an equation for a circle like x squared plus y squared equals 4. Well, this is a circle of radius 2, and so there's 2 and minus 2 and 2 and minus 2. But I could ask, like, oh, well, what's the slope of the tangent line to that curve right there at, say, you know, pi over 4 or 45 degrees or something like that? And, well, gosh, you know, one way to go about this is I could solve for y and in terms of x and do my work that way. And so let's suppose we do that. We solve for y, so we have y squared equals 4 minus x squared. And we want the top half of the circle, so that's when I take the square root, I want the positive square root, 4 minus x squared. Now I could take that derivative, y prime, or dy dx, however I want to write it. And that is, using the chain rule, my outside part is the square root, so that's something to the 1/2. So I have 1/2, that's something to the negative 1/2. Well, that something was 4 minus x squared. And then times that derivative of 4 minus x squared, so I'll write that, 4 minus x squared there, that derivative. And so that's equal to 1/2 4 minus x squared to the negative 1/2 times, looks like negative 2x. So if I put that all together, I get y prime is negative x over the square root of 4 minus x squared. So there's y prime. Okay, I'll go to page 2 here, and we'll use implicit differentiation. So we started with x squared plus y squared equals 4. Now, the idea is just take the derivative with respect to x of everything. Now, because see, what we have is we have one function of x on the left side. It's an implicit function, but it's a function. So, you know, I have some function of x on the left side, and it's equal to some other function of x on the right side. Okay, now 4 is a constant, so it says, oh, this function on the left turns out it's a constant, but I have this, and so if I take the derivative, those should also be equal. Right? If it's the same function, it should have the same derivative. And so that's kind of what we're doing with the implicit differentiation. We're saying, oh, well, take the derivative of everything over here and take the derivative of everything over here. Well, on the left side, this first one, you know, so I have derivative of x squared dx plus the derivative of y squared dx. That's the important part there, is the x. And equals, now derivative of 4 with respect to x, 4 is a constant, so I get 0. And so here, derivative of x squared, well, that is just 2x plus, but now here, see, I have to use the chain rule because I start with just, you know, I look at it and I don't have to make it difficult. I just look at it and I say, oh, well, what is that derivative? Usually, if I were, say, taking it with respect to y or something like that, right, that's just 2y. But then it is the chain rule, because y here is a function of x, so I need dy dx, and then equals 0. But now you see, when you do this, you should always be able to solve for dy dx, and so I'll solve for dy dx. Got lots of different ways to do it, but 2y dy dx is equal to negative 2x. Whoops. And then divide both sides by 2y, and I get my dy dx is equal to negative 2x over 2y, but that's equal to negative x over y. Okay, so we got negative x over y. Is that the same thing we got back here on page 1? Well, actually, yes it is, because look there, that is the function y. This is equal to negative x over y. Pretty nifty. And if I wanted to know that derivative, you know, at this particular point, well, I'd have to know what that point is, but if, say, that angle is at 45 degrees or pi over 4, I know that is the square root of 2 square root of 2 is that point right there. Right, and you can check that. If I square them, I get 2 plus 2 is 4. And certainly if the lengths are the same, then that is the angle of pi over 4 or 45 degrees. So that's the point. And so I can put it into either, you know, this function here, the y prime that I have there, and just put the x in, or I can put it in here, in which case, you know, I have negative square root of 2 over the square root of 2, I get negative 1. Well, I shouldn't have put an equals there. Sorry about that. This is y prime at square root of 2 equals, and that's the negative square root of 2 over square root of 2, and that's equal to negative 1. Okay, so I get it that way, or you know, I could have done it here with this, and again, that's if I want y prime at the square root of 2. Well, see, I would need to know its y value, right? But I could get that even up here with this original, or I could solve for what the y value is given x equals square root of 2. But once I have that x and y value, I get my negative square root of 2 over the square root of 2, which is negative 1. So I can get that derivative that way, and that's the idea of implicit differentiation. We'd start with this equation where we've implicitly defined y as a function of x, take the derivative of both sides here with respect to x, and just remember to use the chain rule like we did here, and this will work pretty much every time. You should be able to get, you know, bring dy dx, you know, everything involving that to the left side of the equation, so, you know, put everything else on the right side, factor out the dy dx. It should always just be dy dx. You shouldn't have like dy dx squared or anything like that. And so you should be able to always make this work. And then to get a particular derivative, well, you would need some x and y values, but that's true for any function. Okay, so that's an intro to implicit differentiation.